I'm going to talk a little bit about ellipses here in this mini lecture. And so first, a definition that I give right here at the beginning. An ellipse is a set of all points in a plane, so in a flat surface, such that the sum of the distances to two fixed points is a constant. So two fixed points, those are called the foci of the ellipse. So the word foci is just the plural of the word focus. So we have one focus, we have more than one foci. And an ellipse has two foci. So those are fixed points. To draw an ellipse, we can imagine a string at the end of a fixed length, a string of a fixed length. So we have a set amount of string with thumbtacks at each end. We put the thumbtacks in a piece of cardboard and use a pencil to hold the string taut. And then we move the pencil wherever it can be moved. So here in this image, F1 and F2, those are my two foci. And this blue thing here is the string, and we've got the pencil. And so we would hold that string tight, and if we trace around with this, we end up tracing out this oval shape. And that's what an ellipse is going to be. We want to figure out what does the equation of an ellipse look like. And to do that then, we're going to represent this length with a variable, and it's a little weird. We're going to call the length of this string 2a, not just a, we're going to call it 2a. And that seems a little weird, but trust me, it works better that way. So we're going to start assuming that I have an ellipse that's centered at the origin, that's the point 0, 0, and it has its foci evenly spaced from the origin along the x-axis. And we're going to represent the distance from the origin to each focus as c. So we see that down here. The center would be this point 0, 0. I have one focus that's c units to the left, so its coordinates would be negative c, comma 0. And then another focus is c to the right, so that would be positive c, 0. The string, remember, if we would hold the pencil right up above the center, the string has length 2a. This is sort of why we did it that way. So one half of the string is a going up, and the other half is a going down. We're also then, we've got these two sides are c. We're going to label this side in the middle as b. Remember then the Pythagorean theorem says if I square the hypotenuse, that's the sum of the other two sides squared. So a squared equals b squared plus c squared, or I could subtract c squared from both sides, and that would give me b squared equals a squared minus c squared. That's going to be important later on. So with that setup, the key idea then, if I move the pencil here to point P that's away from the top, the sum of the distance from P to F1 and the distance from P to F2, that's the total length of the string. That must equal that total length 2a. To find these distances from P to F1 or P to F2, we're going to use this distance formula that we've talked about before. x2 minus x1 squared plus y2 minus y1 squared, and then I take the square root. And so we're going to apply that distance formula from P to F1 and then from P to F2. And those two distances have to add together to equal that total length 2a. So from P to F1 I subtract the x's. X minus negative c, and then the y's. Y minus 0. And then those get squared and added together. And then from P to F2 the same sort of thing. Of course, minus a negative turns into a plus. Y minus 0 is just y. We get this equation. Now, we're going to clean up this equation. We're going to get rid of the radicals. To do that, I'd have to square both sides. But before I did that, I'd have to move one radical to the other side and then square. That would get rid of one radical, but then I'd have a quantity squared on the right, and that would get really messy and ugly. There's a lot of algebra we have to do. And if you really want to find out, you could probably Google derivation of the equation of an ellipse, and you could find all the details somewhere like that. I'm going to skip the gory details. Eventually we get to something that looks like this. So when we combine like terms and do a bunch of squaring, we get a squared minus c squared times x squared plus a squared times y squared equals a squared times this a squared minus c squared. But back on the other page, we said, well, b squared was just equal to a squared minus c squared for this ellipse. That's when we had that triangle, up in the middle. So instead of a squared minus c squared, I write b squared in both places. Then, to just make this look nicer, I just decide to divide both sides by a squared and by b squared. So I put that in all the denominators. and we get this rather clean equation, x squared over a squared plus y squared over b squared equals 1. And we call that then the standard form for the equation of this horizontal ellipse. Now, one thing about this, remember we use this pencil to hold the string taut. Maybe we move the string all the way over here. So if I had those blue lines, they would add up to 2a. Imagine actually bringing that all the way down here to the x-axis. The string would go around that point and back here, and so it would be overlapping itself here. So I'd count this part sort of twice, but then this part I've labeled with x isn't counted at all. But that's actually the amount of the overlap. So if you imagine sort of taking out the thumbtacks and holding the string tight across the ellipse, it would totally just cover exactly this middle of the ellipse. It would go all the way across the x-axis. So the distance across the whole ellipse is 2a, so that means each half of the ellipse has a distance of a. And so we have these distances for an ellipse. A occurs in 2 places, well 4 places actually. A is halfway across and halfway across, but it's also this distance here from the focus up to the top of the ellipse. B is this distance across and across if I'm going up and down, and C is the distance from the center to the origin. So A is out to the sides, B is up and down like this, and C is the distance to the focus. This is called the major axis if I go across this length 2A. B is called the minor axis. Major is longer than the minor axis. One thing I didn't put in the notes here, but if I look at these points, at the end of the major axis are called the vertices of the ellipse. Each of those is called a vertex. And of course the points that we would have here, I should probably make those blue. Remember, those are my foci. That would be F1 and F2. So I guess we could call this V1 and V2, vertex 1 and vertex 2. And this distance, again, is sometimes called the focal length. How far is it to the focus? So this is the standard form for the equation of this horizontal ellipse centered at the origin. It always looks like this here. Now, what if we changed and we said, okay, it's centered at the origin, but now I want the foci to be along the y-axis instead of the x-axis. Almost all the calculations work out the same way, except the A and the B switch. So the major axis is now vertical and the minor axis is horizontal. So I get x squared over b squared plus y squared over a squared equals 1. Otherwise it looks, just the a squared and the b squared have swapped there. Now, when we look at an example of this, the a squared and the b squared, though, are just numbers. So how do I know which one is a squared and which one is b squared? Well, for an ellipse, we have to have a greater than b. The major axis has to be longer than the minor axis. So, in general, a squared is going to be bigger than b squared. That's assuming that both are greater than 1, but that's not going to be an issue for us. So, as an example here, graph the ellipse with the equation x squared over 25 plus y squared over 16 equals 1, and find the coordinates of the foci. Now, one thing, eventually, when we get to next week and we look at the equation of a hyperbola, since that's plus, that means this is going to be the equation of an ellipse. So that's something I noticed first. And for an ellipse, I know a squared has to be bigger than b squared. So what that tells me here then, which one of these is bigger? Well, 25 is bigger than 16. So I'm going to have a squared is 25. What's going on with that? A squared is 25, and b squared is 16. So that means when I take the square root, I get plus or minus 5. I would get plus or minus 4. And what I look at then, where did this a come from? It came from x. So that's how far I'm going to move in the x direction. And this b squared, well, that came from y. 16 was with the y. So that's how far I'm going to move in the y direction. And I'm going to start at the center. And we haven't dealt with other centers yet, but since it's just x squared and just y squared, the center is going to be the point 0, 0. So my center is the point 0, 0. I'm going to move 5 in the x direction. So I count over 5. 1, 2, 3, 4, 5. And then 5 in the y direction from the center. 1, 2, 3, 4, 5. From the y direction, I go up and down. So I go up 4 and down 4 to get the points on the y-axis. Now, you don't have to do this next step. For hyperbolas, we will. I sometimes find it makes it easier if you're drawing these by hand. What you can do then is you can sort of just make a rectangle that goes through these points. And that helps me draw this because then the ellipse has to fit inside this rectangle. So it comes up here to this point, it comes over here to this point, comes down here to the bottom, and then back over and completes it. Okay, so that would be the graph of the ellipse. And now I'm supposed to find the coordinates of the foci. So to find the coordinates of the foci, I need that value c. So for an ellipse, here's how I remember. For a hyperbola, it's going to be a little bit different. For an ellipse, the foci are on the inside of the ellipse. They're always on the inside. So A is out to the vertex. C is going to be in here somewhere. So that means A has to be bigger than C. So if I look here, I know what A squared and B squared are. So which, no, that's not what I want. Oh, where's my, oh, there. So A squared and C squared. Which one's bigger? A squared is bigger. So I'm going to have to add something to the C squared. Okay, so A squared is going to equal C squared plus B squared. A squared is 25. B squared is 16. So now, oops. So now I'm just going to subtract 16 from both sides. So I'm going to get 9 equals C squared. So C is going to be plus or minus 3. And again, since this now is a horizontal ellipse, that's how far I'm going to move in the x direction. So my foci are going to be at -3, 0, and at +3, 0. Okay. So this next one now, same sort of thing. Since it's a plus here, that means it's going to be an ellipse. So I have to have A squared greater than B squared. So for this problem then, A squared is going to be 49 and B squared is going to be 16. So A will be plus or minus 7 and B will be plus or minus 4. But this 49 came with the y. So the 7, that's how far I'm going to move in the y direction, and the 4 is how far I'm going to move in the x direction. And again, move from where? Well, my center is again going to be the point 0, 0 because it's just x squared and it's just y squared. So if I plot these points, I move 7 up and down from the center, and I move 4 left and right. I can make a box. That's sort of optional, but it helps me graph it more accurately. And it's going to be essential when we do hyperbolas eventually that I make this box. So you might as well get in the habit of it. So my ellipse is going to look like this. All right, well, we don't always have ellipses centered at the origin. If the ellipse has its center at the point hk instead of the origin, then x squared gets replaced with x minus h squared, and the y squared is replaced with y minus k squared. So for a horizontal ellipse, it looks like this. Instead of just x squared over a squared, it's got x minus h squared. And instead of y squared over b squared, it has y minus k squared. Notice for a vertical ellipse, the a squared and the b squared just switch. How do we know which is which? A squared has to be bigger than b squared. So here, my center is at hk. That's not necessarily at 0, 0 anymore. A is how far I move here for a horizontal ellipse. A is how far I move in the x direction. So I move a to the left and a to the right. That means this k, the y coordinate, stays the same when I move over to these vertices. But the x coordinate, I have to move to the left. That's subtracting a to make it smaller. And to get to this way, I have to make a bigger, h bigger, so I add a. To get these points here, there I'm going up or down, so the x coordinate stays the same and the y coordinate changes. If I go down, I subtract. If I go up, I add. So the center's at hk. I still have my major and minor axis. They have lengths 2a and 2b, right? 2a is all the way across here, 2b is all the way across here. The vertices, I start at h and I either go a to the right or a to the left. For the foci, I again just move left or right, so only the x coordinate changes. The y coordinate stays the same. For a vertical ellipse, this stuff's all the same, but now for the vertices, I have to move up or down. So the x coordinate stays h from the center. The y coordinate, I have to add a or subtract a. And for the foci, the same thing, except with c. And to find c, I use this equation, a squared equals b squared plus c squared. Or I usually write it a squared equals c squared plus b squared. Well, I just realized on that last problem, I didn't finish it. Better go back and do that. I was supposed to find the foci here. So, how do I find the foci? Well, I know I'm going to compare a squared and c squared. Which one is bigger? Well, for an ellipse, the a is the vertex. Those are on the outside of the ellipse. The vertices, the foci have to be on the inside. And those are the distance c. So a has to be bigger than c. So I have to add something to c squared. A squared is 49. B squared is 16. I'm going to subtract 16 from both sides. So that's going to tell me 33 equals c squared. When I take the square root, this isn't a nice one. To get to these foci, I'm going to have to move up or down. So my focus 1, I'm going to go down, maybe, negative square root of 33. And for my focus 2, it's going to be 0, and then the positive square root of 33. All right. So I think I already talked about this page. You might want to print this page out and keep it sort of separate as you're working on problems from this. It's a good resource. So let's try to graph this equation here. Okay, so what we've got there, since that's a plus, that means it's an ellipse, and that means a squared has to be bigger than b squared. Okay, so the other thing I see is my center. For my center, I look at these values. And I have to sort of think, what would make those equal to 0? What would I have to put in for x to get 0? I'd have to put in 1. 1 minus 1 would be 0. What would I have to put in for y to make this 0? Well, I'd have to let y equal negative 2. So that's my center. My a squared is 16. My b squared is 4. So a equals plus or minus 4, and b equals plus or minus 2. The 16 was with the x, so that's how far I move in the x direction. This then is how far I move in the y direction. But I start at this center, which is the point 1, negative 2. So be sure you make note of that. So now I'm going to move 4 in the x direction. So I move to the right 4. That's going to be over here at a y-coordinate of 5. Notice that's 1 plus 4 is 5. And then if I start here and I move to the left 4, 1, 2, 3, 4, I end up at negative 3. 1 minus 4 is negative 3. And then for my b, I'm going to move 2 up and down in the y direction. If I go up 2, I get to 0. If I move down 2, I get to negative 4. And then I'm just going to connect those points, connect the dots. I have to stay inside this rectangle. So I would get my ellipse looking like that. To find the foci, I have to find c squared. So a squared and c squared, a is all the way to the vertex, c is going to be to the focus, which is on the inside. So a is bigger than c, so I'm going to have to add something to c squared to make them equal. Oh. B squared is 4. I subtract 4. So c would be plus or minus square root of 12, but I can simplify that. I can take the square root of 4 and get 2 square root of 3. So my c is plus or minus 2 square root of 3. This is a horizontal ellipse, so that's how far I'm moving in the x direction. So I'm going to keep the y-coordinate of the center, but I'm going to change the x-coordinate. So the y-coordinate is going to stay at negative 2. The x-coordinate is going to start at 1, right? That's the start of the center. But it's going to go up or down by this 2 square root of 3. Okay. All right, this other example here, again, since this is a plus, that's an ellipse. That means a squared has to be bigger than b squared. For my center, I look at the numerator here, and I say, what would I have to put in to get 0? I'd have negative 3 and negative 1. It's just the opposite of those numbers. A squared is always bigger than b squared, so that means a squared here is going to be the 9. It's going to be a vertical ellipse. So a will be plus or minus 3. B will be plus or minus 2. And the 9 came from the y. The 4 came from the x. So my center is at negative 3, negative 1. That's over here. I'm going to move 3 in the y direction. So I go 3 up and down. I'm going to move 2 in the x direction. So I go 2 left or right. So when I fill that in, there will be my ellipse. To find C, my focus, remember A is all the way to the vertex, C is on the inside. So C is smaller than A, that means A squared is bigger than C squared, so I'm going to have to add something to C squared to make them equal. A squared is 9, B squared is 4. I subtract 4 from both sides, I get C squared is 5. So C is just plus or minus the square root of 5. But this is a vertical ellipse, so when I move up or down, the x-coordinate of the center stays the same for the focus. So the x-coordinate of the center started at negative 3. The y-coordinate starts at negative 1, but I'm going to have to go up or down to get to the focus by the square root of 5. So it becomes plus or minus the square root of 5 for those coordinates of the foci. All right, well, sometimes we're given the equation and it's ellipse, but it's not in standard form. When it's not in standard form, we can use completing the square to put it in standard form, and then we can graph it or find the foci or anything we want to do. Now, to complete the square, what's important is first we want to get all the x stuff together. Then we want to get the y stuff together. And we want the constant on the other side. All right. So we're going to get the y stuff together, x stuff together, get the y stuff together, and move the constant to the other side. So I'm going to want to move that over there. And let's see. So my x stuff, I've got 16x squared plus 96x plus 25y squared minus 50y. I'm going to add 231 to both sides. Now, to complete the square, I want my coefficient of the squared term to be 1. Often what we did here then is we would divide everything by 16. The problem is I want y squared to also have a coefficient of 1. So to do that, I'd have to divide by 25. That's not going to work. So we do something a little bit different. Whatever's in front of the x squared, we're going to factor that out from the x stuff. So I'm going to take out a 16 from everything here having to do with x. So 16 divided by 16 is 1, so I would just get x squared. If we take 96 divided by 16, I get 6, so that would be a 6x. For the y's, I take out the 25, and I get y squared minus 2y. It equals 231. Now, I'll have something to say about that in a second, okay? Now, to complete the square, remember, I take half then, once I get a 1 for my squared, I take half the coefficient of my linear term, so half of 6 or half of -2, and then I square that. So, I didn't leave myself much room to do this. So 1/2 times 6 squared is going to be 3 squared, or 9. So I'm going to add 9 in that set of parentheses. Over here, for my y's then, I'm going to have to take half of 2. So half of 2 squared is going to be 1 squared is going to be 1. So I'm going to put in a plus 1 there. All right, now what's a little bit tricky with this is you think you added 9 to the left, so you would think you'd add 9 to the right, but that's not exactly true. You really added 16 times 9 to the left. And 16 times 9 is 144. And here you thought you were adding 1, but that's actually 25 times 1, which is 25. So that's a little bit tricky. I'm going to factor this. We're going to get x times x. The 9 is going to be 3 times 3, and notice 3x and 3x gives me 6x. For my y's, I'm going to factor. Y times y gives me the y squared. The 1 has to be 1 times 1. And if they're both negative, then that all works out. If I add this, I get what? 376 plus 375 plus 25, I get 400. Now, for standard form, we want that to be 1 over there. We want something squared plus something squared equals 1. Let me rewrite this, though, here first. So 16 times x plus 3 squared plus 25 times y minus 1 squared equals 400. Now I'm going to divide by 400. But that's going to make me divide both parts of this side by 400 as well. So when I look at this, I have to think, does 16 go into 400? Well, we can divide. Use your calculator. If we take 400 divided by 16, we get 25. If I take 400 divided by 25, I get 16. And there's my nice standard form. You're going to have to practice that a little bit. Look at the problems in Math Excel for a couple more examples of that. One other type of problem, sometimes we're given like a graph in the ellipse or information about the ellipse, and we're supposed to find the ellipse itself. So for something like this, now I have to sort of figure out where's the center, what's A, what's B, and then I'm going to need C for the coordinates of the foci. So my ellipse here looks like I'm going across this way. I'm going across this way here. So my center looks like it's at the point -3, 1, right? So it's over 3 to the left and up 1 from this point 0, 0. 1, 2, 3, 4, I'm moving 5, this 5 left, 5 right from the center. I'm moving 4 up and down. So remember, A has to be bigger than B. So that tells me A here is 5 and B is equal to 4, and it's going to be horizontal because it's moving more left or right than it is up or down. So if it's horizontal, then it's going to be x minus h squared over a squared plus y minus k squared over b squared equals 1. And I'm just going to remember this be h and this be k, but it has to be subtracted, so be careful. When I do this, when I do x minus h, it's x minus -3. Minus a negative becomes a positive. So x plus 3 over 5 squared plus y minus the y coordinate of the center is just 1, so I don't have to worry about that becoming positive. Oops, forgot my squared over there. Over 4 squared equals 1. So we get x plus 3 squared over 25 plus y minus 1 squared over 16 equals 1. That's the equation. To find the foci, I need C. We've done this a few times already. I know a squared is bigger than c squared, so I'm going to have to add something there. So how do I get a squared and b squared? I know what a is, I know what b is. A squared is going to be 25. B squared is going to be 16. So I get C is plus or minus 3, but that's how far I'm going to have to move in the x direction. So my center starts at -3, 1. Since I'm moving left or right, the y coordinate stays the same. I'm going to have to add or subtract 3 to get the foci. Since that's not a square root, I can actually figure that out. -3 plus 3, 1. That's the point 0, 1. -3, oops. Minus 3, 1. That would be the point -6, 1. So those would be the foci. Okay, so who cares about ellipses? Well, ellipses have some very special properties, a couple of them. One, there's this reflective property where if I start any beam essentially at one focus of the ellipse and it hits the side of the ellipse, it immediately gets reflected in a straight line to the other focus. So this red beam would be one beam of light or beam of sound or something like that. This green beam would be another one. This gray beam would be another one. This yellow beam would be another one. So all beams that start at one focus get reflected immediately to the other focus. It focuses the beams essentially. This is used sometimes in medicine to destroy kidney stones or gallstones. It uses shock waves of sound that get bounced to where the kidney stones are located. So the person is placed so that the kidney stones are at this other focus, and then sound waves emanate here and get reflected and destroy the kidney stones. There are whisper chambers or whisper rooms where you can stand in two locations, and if somebody is at one focus and whispers, somebody at the other focus can hear that whisper perfectly clearly, even though it could be very far away where that wouldn't normally happen. You sometimes see that kind of thing at science museums. Also, when a planet orbits a star, or even if the moon orbits the Earth, the orbit is an ellipse with the star at one focus of the ellipse. So these would be the two foci. The sun is at one focus, the planet like the Earth would be at the other. Now, just to show this ellipse is a little more oval shaped than most ellipses are. The planets that, even though like for Earth, even though its orbit is elliptical, it's almost circular. If you think about it, a circle is just an ellipse where the major and the minor axis are the same. So that means the Earth is closer to the sun for one point of the year, and then 6 months later it's farthest away from the sun. You might think then, oh, well, that's the summer then when we're closest to the sun. Well, that's not really why summer and winter happen. Summer and winter happen because the Earth's axis tilts. During the summer, the northern hemisphere is facing the sun more directly. In our winter, the southern hemisphere is facing the sun more directly, and that's what causes the difference in temperatures. You know, when it's summer here, it's winter in Australia. And actually, when we're closest to the sun, that's more the winter in the northern hemisphere. So it's not what you would necessarily think. All right, well, that's how ellipses work, and we'll talk about some other curves like this next week.